Well, talk about exponentials.
Okay.
Exponential functions are typically, in other words, if I tell you that y equals 2 to the x power, that's going to look like that.
Right.
If I tell you y equals 3 to the x power, it's going to look like that. Very similar. In fact, they both go through this point right here. So y equals 3 to the x might look like that. Why do they both go through the same point? Because when x is 0, both of these are equal to 1.
Okay.
When x is 0, because any number to the 0th power is 1. So all exponential functions go through this point 0, 1. Okay.
Right.
If there's no multiplier in front. Now some of yours have multipliers in front. But this is a key consideration for exponential functions. In other words, we can figure out 2 points on each of these curves quite easily. The first one, label the x or y intercept and at least 2 other points. Okay? We've got y equals 7 times, let's cover one other here. If I said, what is 1/2 to the x power? That doesn't look like the others. It looks the opposite. It looks like this.
Right.
Because this number is less than 1. When you take a number between 0 and 1 and you exponentiate it to whatever power, it gets smaller. If you square 1/2, it's equal to 1/4.
Right.
So as I'm going to the right on the x-axis, in other words, as this number is getting bigger, my y keeps getting smaller.
Right.
So whether or not your curve is going to look like this or this depends totally on whether what's inside the parentheses is less than or greater than 1.
Okay.
Okay? In this case, it's less than 1. So I know this curve is going to look something like that.
Okay.
Does it have any x-intercept?
No.
No. It's going to approach the x-axis all the way out to infinity, which means it's never going to cross the x-axis. So there's no x-intercept. There is a y-intercept. What does x, and remember y, the intercept for y comes when x is equal to what?
0.
Okay, so what's the solution to that right there? That's my y-intercept.
Your y-intercept? Okay, so...
Because y-intercepts come when x is equal to 0. So if I plug in x equals 0 and come up with a number for this, that's my y-intercept. What is that number?
5.6.
Actually not. Remember, any number to the 0th power is equal to what?
So 7.
It's equal to 1, so my y-intercept comes right there. That's 7.
Gotcha.
Okay? And I know this curve is going to look like that.
Okay.
In other words, if x were 100, way out here, well, this number is going to be extremely tiny.
Okay.
If you take 0.8 and square it, it becomes 0.64. Square it again, it becomes 0.36. So if you keep exponentiating this number that is less than 1, keeps getting smaller and smaller.
Right.
Okay? So I know this is the shape of my curve, and I know it goes through this point. What is another very easy point to get? Because it wants 2 points. Actually, it said it wants 2 other points. It says label the x or y-intercept. Well, we only have a y-intercept. We labeled it. And at least 2 other points. So what's a real easy point? X equal to what?
X equal to 1.
Okay. What's y equal to when x is equal to 1?
6.
7 times 0.8.
Oh.
5 points.
So 5.
See why it's 5.6?
Yeah.
Okay. What's another easy point to figure out?
Hold on 1 second. Let's see.
About 2.
2? Yeah, so.
We've already used 0. We've already used 1. Probably best not to get into negative numbers if you don't have to. So let's use 2. So what is 7 times 0.8 squared? What's 0.8 squared?
That just 0.8 squared?
Let's always do your exponential first.
0.64.
Okay, and then times 7.
I got 4.48, so like 4.5.
So this point right there is 2 comma 4.48. There's your other 2 points.
Okay.
Okay? And that's the way you're going to do all of these. You're going to figure out what the general shape is. You're going to figure out where it crosses the y-axis. And then you're going to figure out 2 other points by substituting the easiest numbers you can for x. I could have used an x of 5, but that would have made the mathematics much harder, the arithmetic of it.
Right.
Okay? So let's do 2. Now, 2 is different in one huge respect. What is it?
Number 2?
What's different about 2 from 1?
It's greater than 1?
Yes, which means the shape of our curve is going to be like that. As x gets bigger, this thing gets bigger. When you start squaring and cubing numbers bigger than 1, they always get bigger. So as we go to the right, it's got to go through there. Where's the y-intercept? Again, there's no x-intercept because this is an exponential function. Where's the y-intercept?
At 10.
Okay. Make it right there. We'll call that 0 comma 10. And we know our function is going to do something like that. And this is always going to be asymptotic to the x-axis. Why? Because as x gets smaller and smaller, as x gets negative, well, this whole thing gets closer and closer to 0. In other words, if you give an x of a -1, I'm at 9. If I give an x of a -10, I'm probably down here closer to 1. And if I give an x of a -100, I'm almost at 0. The important thing to remember is what the shape of these curves are, whether it goes from left going up or going up going down. all of which is predicated on whether this number is greater than or less than 1.
Okay.
Okay, give me another point on this curve. We need 2 other points.
We could do -2.
Try not to use negative numbers if we don't have to.
So just 2.
How about 1?
Okay, that works.
Yeah, you always use the easiest numbers you can use. We've already used a 0, so we can't use 0. But we can use 1.
So,
What is y when x is 1?
13.
Okay. So this point's on the curve, 1, 13. Pick another number for x.
You could do 2.
2 would be plenty easy, right?
Mm-hmm.
Okay, so we can do 2, but just for switching it up, let's do -1.
Okay.
What is this number when x is -1? What does it mean to be 10 times 1.3 to the -1?
I don't know.
Well, a negative exponent means you just switch it. This part here is the same as 1 over 1.3 to the +1. That's what the negative exponent means. In other words, 1.3 to the -2 would be 1 over 1.3 to the 2. So that's all you do with negative exponents. Okay? Well, I still got this 10 here. So it would be 10 divided by 1.3. What's that number?
That is 7.6.
Okay? So if I go to -1, this number here is 7.6. So -1, 7.6. And there's your 2 other points.
All right, perfect.
Okay? Number 3.
Okay. Number 3. Log of 5.
First of all, log functions are the inverse of exponential functions. So if exponential functions always look like that, if that number is greater than 1, log functions always look like that.
Mm-hmm.
And they have a similar characteristic in that this point's always the same. The log of 1 is 0.
Right.
No matter the base. In other words, if this was y equal log base 7 of x, it would still go through that same point, 1, 0. No matter the base, as long as the base is greater than 1, it's going to have this shape.
Okay.
Is there any y-intercept?
No.
But there's an x-intercept, and we just found it.
Okay, so for the log of 5, it would be at 0, 5, or 5, 0.
What is
No, 0.
the log base 5 of 5?
Wait, what was the question?
What is this?
I don't
It's
remember.
always 1.
Okay.
The log base 17 of 17 is 1. The log base 1,000,000 of 1,000,000 is 1. So the log base b of b is always 1. So that's a great second point to use, right? In other words, if I go out to 5, I know that that's got to be 1. So this second point is 5 comma 1. So always on equations like this, to find a second point, you can always substitute the same number as the base.
Okay.
Okay. Now, a third number.
Um.
I've already tried 1. I've already tried 5. 2 is not particularly easy, but a number that is easy is 25. And I'll explain in a minute.
Okay.
If we let...
It would just be 5, right?
No, it would be 2. In other words, what's the solution to that?
Oh. It'd be 2 because 5 squared is 25?
Yes. In other words, if I give you this equation to solve, you solve it by the number on the far left raised to the exponent on the far right equals the number in the middle.
Correct.
So the log base 5 of 25 equals 2. So there's our second point. When I go out to 25, I know that this has risen to 2. So 25 comma 2 is our second point. The reason I got to go all the way out to 25 is notice that if I said what is the log of 10 base 5, that is not a whole number. That is a fractional number. You'd have to look that up on your calculator, and it would be an approximation. It would be an irrational number. So if I want whole numbers to make it easy to plot, and I'm doing these, I'm going to start with 1 to get this point, and then I'm going to do the first power of 5 to get this point, and then I'm going to do the second power of 5, 5 squared, to do that point.
Okay.
Okay?
Okay.
Starting value, growth or decay factor, and the growth or decay rate. Starting factor is always when x is 0. Usually,
right.
x is the number of years. In fact, it's not usually x, it's usually the variable is t. When we're applying these, that's usually in years. It can be in days, it can be in seconds, it can be in anything. But the starting value comes when that variable is 0. Right?
So it's 75
right.
in this
When
case.
time is 0, that's when it starts. So when x is 0, y of 0, that's 75. So that's the starting value. What is the growth or decay factor?
Wouldn't that be 1.242?
First of all, it's growth because it's greater than 1. If it was less than 1, if it was like 0.98, then it would be decaying.
Right.
And what is the growth rate?
The growth rate would be 142. Oh, no, point.
I'm not exactly sure what they're wanting here, but the growth rate is 42%.
Okay.
In other words, it's increasing by 42% every single year if x is in years.
Mm-hmm.
And that's why it's always 1 plus the growth rate. So to get a 1.42, the growth rate must have been 0.42. Okay?
Right.
If I were to make this 0.98 instead,
Mm-hmm.
now the initial value is still 75. The growth rate is 0.98. Actually, excuse me, it's a decay rate.
Which one are we on? Or are you
Just
just doing
making
it
one
again?
up just to show you a difference. And
Gotta look.
the decay is minus 2%. Okay, so you understand what growth or decay factor is, and you understand what growth or decay rate is.
Yeah.
Okay? Let's look at number 5. Starting value.
Starting value is 99.
Is it a growth or decay, and what is the growth or decay factor?
It is decay, and it's 0.78.
And what is the decay rate?
It is 22%.
You got it. Number 6. What's the starting value?
0.
If I make x equal to,
Or 1.
it's 1. There's an implied 1. In other words, if I'm going to say all my equations look like this, then A is 1 here.
Okay.
B is 1.1. Okay? But regardless, if I let x equal to 0, I always get my starting value. And if I let x equal to 0, y is equal to 1.
Right.
Growth or decay factor?
Growth.
1.1. Okay? And what is the growth rate?
10%.
Okay. Okay, so if we start out with this is our standard form,
Mm-hmm.
they want us to come up with an equation in this form that has all of these conditions. Starting value of 65. I'm not quite sure what 7 is saying. I feel like it's...
Is it talking about like
No, we've got a page thing going on here. Notice 9 has nothing in it. Do you have this page in front of you?
Weird. Yeah, I didn't notice
What's
that.
7 say?
7 says starting value of 65 and value. Oh, that's weird. I think it should. I don't know.
Okay.
I think some of that should be over on.
Right. Some of it's obviously one of those starting values goes up here. That starting value, that value equal 5 must be 9.
Okay. I'm going to put that over there.
And we've got 3 different things. We can just make them up if you want. I'm going to assume that the increasing at 27% goes with number 7.
Okay.
Okay? So, if we have a starting value of 65 and we're increasing at 27%, what's our equation?
Y equals 65 times .27. 1.27.
There you go. Notice that if I were to just put .27, I would have something that was decreasing because it's a number less than 1. So
Right. So you add them.
Right. You always add it or subtract it from 1. Okay? If it's increasing, you add it. If it's decaying, you subtract it. So that's the answer for that, presuming the starting value is 65 and we're increasing at 27%. Now let's do number 8, and let's assume 8, I know it has a starting value of 70, and let's go ahead and use the decreasing at 32%. So what's that equation going to be?
Y equals 70 times 0.32 to the power of x.
Remember, you got to subtract that from 1.
That would be 6.68.
0.68. Now notice this is less than 1, so it's decaying. But remember, when they give you this increasing or decreasing, that's the rate. That's not the number that goes in the parentheses. Okay?
Okay.
And the third problem will have a starting value of 5. And we'll be increasing at 12%.
Right.
And
So
you may have to change these if I'm not putting these together with the right problems. I mean, before you turn this in, you need to know which of these go with which problem.
Right.
So
Y equals 5 times 1.12 to x.
pretty straightforward.
Yep.
Okay, geometric sequences. If a sub 1 equals 5 and a sub n equals 2, a sub n minus 1, write the first 5 terms of this sequence.
I have no idea.
What's the first term of the sequence?
5.
Correct. And it's a geometric sequence, so every term is going to be some multiple of the previous term.
Right.
So if a sub 1 is 5, what is a sub 2? It's 2 times a sub 1. A sub 2 minus 1. So what is a sub 2?
A sub 2 is
Let's go over the...
5 times 2?
Well, hold on. A sub 2 is 2 times a sub 2 minus 1. Right? In other words, a sub 2, n is 2. So a sub 2 is now 2 times, well, this is a sub 1. What's a sub 1?
5.
Okay, so a sub 2 is 10.
Okay.
Okay, now that's all I really need, right? Because I know it's a geometric sequence, so what's the next term?
20.
And the next term?
That would be the total 30.
Every term's being doubled.
40.
And the next term?
80.
There's your first 5 terms of the sequence. Now, if we wanted to do it the hard way, let's do it the hard way just so you understand. The third term, a sub 3, is equal, based on this, to 2 times a sub 3 minus 1. That's what the n minus 1 means, which means it's 2 times a sub 2. Well, this is a sub 2, so that's how we get 20.
Oh, okay, get it.
As long as you know the previous term, this is called the recursive definition.
Okay, I remember that.
You have the explicit formula for a geometric sequence, and then you have the recursive formula. They're giving you the recursive formula here. All right, let's go to the next page. For B and C, write the explicit rule for that sequence, because what they gave us was the recursive rule. What's the general formula for the explicit rule for the nth term of a geometric sequence?
Oh, I don't remember.
Equal to the first term times the multiplying factor to the n minus 1. In other words, let's take that sequence we were looking at.
Okay.
What is the third term based on that?
20.
Well, let's solve it. We got a sub 3 equals a sub 1, which is 5. What is the common ratio?
5.
2. We're doubling every term, right? That's what R means.
Okay.
R is what are you doing to every term? Every term is being doubled from the previous term. So R is 2. N is 3. I said what's the third term? So it'd be 2 to the 3 minus 1. Well, that's 5 times 2 squared, which is 4. That's how you get 20.
Okay.
Tell me what the 11th term is.
So that'd be a sub 11
Okay?
equals 5 times 2 to the power of 11 minus 1. That equals 5 times 2 to the power of 10 is our number.
2 to the power of 10 is 1024. Just happens to be one I remember. 2, if you're trying to get to 1,000, 2 to the 10th is almost 1,000. And, you know, it goes up 64, 112, 256, 512, 1024 when you're doubling.
Right, and that equals...
Well, and then I got to multiply this by 5.
Right, so 5,120.
Right. That's what the 11th term would be. In other words, by having these formulas, I don't have, if I said what is the 150th term, you could do it on a calculator. You wouldn't have to sit here and double it 150 times.
Right.
So this is the explicit nth term formula.
Okay.
The recursive they gave us. The recursive, just as for your own edification, the recursive is always a function of the previous term.
Okay.
Notice that the recursive, a sub n, is a function of a sub n minus 1. So in the recursive, if I said what's the 150th term, wouldn't be so easy to come up with. because I don't know what the 149th term is.
Right.
Okay? But if you're doing a small series and you're only doing a few terms of that series, it's pretty easy to do it using the recursive formula. And you can have exactly the same series, and they will have an explicit formula, and they'll also have a recursive formula.
Right.
All right? What is the 15th term of this sequence? Well, let's use the explicit, because the recursive isn't going to be that easy to use. We don't know the 14th term. But we do know the common ratio. So what is a sub 15?
Do you want the whole answer?
No, just let's lay it out. I don't care about the number. I just want to make sure you set it up right.
Okay. I put a sub 15 equals 5 times 2 to the power of 15 minus 1.
That's all. That's all you need.
All right.
That's sufficient for me. I know that you can use your calculator at this point.
Okay.
Okay? What'd you do on your end to get rid of all that background static noise that I was hearing?
Is it starting up again?
No.
Well, I have no idea.
About a minute ago, right in the middle of when you were talking, all of a sudden all the sound went good and I lost. Sounded like slot machines were going off behind you before.
Huh.
And it's not the first time I've had it happen, and not just with you. I've had it happen with a lot of students. And I never have figured out what it is. That's why I thought I would ask, is because it stopped all of a sudden midstream for you.
Huh.
Okay.
Interesting.
An exponential curve runs through those 2 points. Find the equation. Well, one of the points is 0, 6. The other point is 7, 9. So immediately, I know if it's an exponential curve, it's going like that, right? It's not going down. So I know that my b is greater than 1.
Right.
Okay, and the general formula is this. So we have to solve for a and b.
Right.
How can I solve for a?
That would be your y-intercept.
Right. But the beauty is that if I let x equal 0, b, regardless of what b is, b to the 0th power is 1. So what's a?
Six.
Yeah. So a equals 6 based on that. In other words, I know this point's on the curve, and that point is where x is equal to 0. So if I plug in x equal to 0, no matter what b is, b to the 0th is 1, so a equals 6. Because I knew that 6 was equal to a, b to the x. So a is 6, and now I've got a new equation since I've solved for a. And I know another point on that curve. What is it? And what do I substitute? Where do I substitute it?
You put it in for...
The point is, the point's 7, 9. So if I'm trying to solve for b,
like how do you get b?
yeah.
I don't know on that.
I know this point is on that curve. Well, this point has an x and a y in it. So let's substitute these 2 points for x and y.
Oh, okay.
Okay, so you get 9, that's the y value, equals 6
Right.
times 7 to the x value.
Okay.
That's only got one variable in it. I can solve it. However,
Okay.
it's not that easy to solve if you're not up on your logarithms. You do need to solve this with logarithms. Whenever you're solving an exponential equation, you want to try to isolate this part of it.
Okay. So you subtract 6 from both sides.
Subtract, I divide.
Oh, you divide.
I'm dividing because I'm going to do the opposite of what the 6 is doing. The 6 is currently multiplying.
Right.
It's not being added. Okay? So if I divide both sides by 6, I get 1.5 over here. I get 7 to the x power there. And I still have to solve that. That's not trivial to solve. That is not an algebraic equation. When your exponent
Right.
is the variable, when your variable is in the exponent, it's an exponential equation. And we require logarithms to solve exponential equations. So how do I solve that we're looking at there?
You do log of base 7 1.5 equals x?
That's one way to do it. Take the log base 7 of both sides.
Oh, okay.
In other words, any equation, you're always allowed to do whatever you want to one side as long as you do it to the other. And that applies to square roots, squaring, taking logs, taking the derivative, taking the integral, all of these fancy things that you haven't even gotten to yet. You can always do it to any equation. As long as you do it to both sides, you can do anything you want. Okay? Well, the beauty of taking the log base 7 of the right side is what? What does that simplify to?
Log base 7?
This side here, the right side of that equation, what does that simplify?
Equals 1.
Equals x.
X.
Actually equals x times the log base 7 of 7. In other words, I can always bring this exponent, whenever I have a logarithmic expression, I can always bring the exponent and put it down on the equation line. But that's always 1. So the right side is immediately equal to x.
Oh, okay.
Okay? That's why we took log base 7 of it. What's the left side? How are you going to get this number out of your calculator? What? Log base 7. In other words, because you took log base 7 of the right side, you got to take log base 7 of the left side. You can't take natural log of the left side and log base 7 of the right. Algebra does not allow that.
So you divide them.
So what's log of 1.5 base 7? How do I get that out of my calculator?
You do log of 1.5. Yeah?
Uh-huh. Divided
I
into
do
the log
log.
of the big number divided by the log of the little number. And when I say big and little, I mean big and tiny. I don't mean the size of the number, I mean the placement of it.
Right.
Okay, in other words, it's always the log of the argument divided by the log of the base. Now, let's do this problem a different way. And I'm going to show you that it's actually a superior way to do it. Instead of taking log base 7 of both sides, let's just take the common log of both sides. Log base 10 of both sides. Okay?
Okay.
Now, the right side, that allows me to bring this exponent down, put it on the equation line. Remember, this is log base 10 of 7 now. This is log base 10 of 1.5. Now, if I divide both sides by log of 7, I get the same answer as I just got, right?
Yeah.
And I never had to worry about this log base 7. Your calculator only has 2 log keys on it for a reason. You're not ever working with log base 7 or log base 13 or log base 2. You're always working with either common logs or natural log. And in all the higher maths, you're working with natural log. And I could have taken the natural log of both sides. The only difference is I would have gotten the natural log of 1.5 divided by the natural log of 7. And guess what? That's equal to the common log of 1.5 divided by the common log of 7. These ratios are always the same regardless of the base. Also equal to the log base 7 of 1.5 divided by the log base 7 of 7.
Okay.
So when you're solving exponential equations, I would always use natural log myself, no matter what the numbers are. It doesn't shorten it any to use log base 7. I'm going to use natural log when I do it, just always, because I'm quite comfortable working with natural log. So this becomes x natural log of 7. So x becomes natural log of 1.5 divided by natural log of 7. There's your answer.
Oh, okay.
Okay? So it seems like it's easier to take the log base 7 of both sides, but not really. It's not really easier. It's just as hard, and it's actually a little more difficult to understand.
Right.
Let's talk about these. You should have learned 3 equations regarding savings accounts. One is the amount that your savings account is worth is always the amount you started with times 1 plus your interest rate raised to the number of years you have it. That's for if it's compounded yearly.
Okay.
If it's compounded more frequently than yearly, greater than yearly, then the amount is equal to your starting amount times 1 plus r over k to the kt, where k is the number of times a year it's being compounded. In other words, let's say you're compounding quarterly. K is 4.
Mm-hmm.
And there's a third one, continuous compounding, where the amount is equal to your principal PERT, P to the RT. Okay? So depending on what your bank is offering, because banks will offer all kinds of rates, one bank might compound yearly, another bank might compound quarterly or monthly, another bank might compound continuously. They all give you different results. Continuous is the best if you're the consumer. Now, this question, the reason I bring all 3 of these up is this question doesn't say what they're doing. It says you're making 3% per year in interest. So I'm going to assume that it's compounded yearly. Okay? There's only two choices here. It's either going to be compounding yearly or it's going to be compounding continuously. They don't say continuous, and they certainly don't say every 3 months or every month or every day. So it's not the middle one. It's not compounded more often than yearly. Since they don't say continuous, I'm going to assume this one. So the amount we're going to have is going to be the starting amount, 650, times 1 plus 3% is 0.03. You have to always convert these to decimals.
Right.
T is the number of years you leave it in there.
Right.
So that equation equals 650 times 1.03 to the t power. So if you leave it in there 2 years, you would have that amount. You leave it in there 3 years, you would substitute 3 for t, and you would have that amount.
Okay.
Answer A, that's the answer.
Okay.
How much money would you have after 10 years? Now you're going to need your calculator for this.
Okay.
Because it's going to be 650 times 1.03 to the 10th power. So on your calculator, take 1.03 and raise it to the 10th power. It gets bigger.
Right.
Multiply that number by 650.
I got 873.54.
That makes sense. That's a pretty low. That's a pretty low interest rate, 3%. 10 years, you wouldn't expect the money to double, but it goes up by about 30%, which is pretty close to what you would expect. Okay?
Okay. I get it.
Okay. 13's the last one?
Yes, sir.
Okay. I don't know. We'll have to, oh, no, I see a 14 on there. Well, we'll do 3 minutes.
Yeah.
Unfortunately, I got a 6 o'clock that I got to go to. But
Okay, that's fine.
we can get started on 13. He's just ordered, after drinking it, there's 1,200 milligrams of caffeine in his body, and then the caffeine leaves at a rate of 11% per hour. What do you suppose my caffeine is going to be? Starting amount is 1,200. Now,
The caffeine.
this is continuous. Notice. I'm not losing 11% per hour. If you think about how caffeine disappears or dissipates in your body, it's a continuous rate. So my regular function is this.
Okay.
In other words, we're going to use the third function that I came up with, this one, because this is, whenever you're decaying, it's almost always continuous rate, not on some time frame that's artificially placed on it by humans.
Gotcha.
Okay? I mean, if you were to study medicine, drugs in the body leave the body at a continuous rate. It's continuous decay. So I'm going to use that continuous there, and it's going to be P is 1,200, E is the number E, R is 11%, 0.11.
Okay.
T is 1 hour. So what is e to the 0.11 power equal to?
It is equal to the caffeine level?
Well, first of all, I did this wrong. There's the equation.
Oh.
Okay? And T is in hours.
Okay. So
at the end of 1 hour, how much caffeine would you have left in your body? Substitute 1 for T.
okay.
What's e to the 0.11 power equal to?
Oh. 0.11.
E raised to the 0.11 power.
E? I'm confused.
Number E, which is 2.71, but there's an E on your calculator, just like there's a pi.
Where's the E button?
What kind of calculator?
Is it like...
You have the TI-84?
Okay. Yeah,
The E is over the divide sign.
Oh, it's 1.11. That's what I got.
Okay. 1.11. Well, there's something wrong here. Because obviously we need to have less caffeine in your body at the end of 1 hour, right? In other words, it should lose 11% at the end of 1 hour. But don't have time to investigate this any further. So we'll have to stop there. And
okay.
I don't know what to tell you here. That's not what they ask anyway. They say give the equation relating the amount of caffeine in his body after a certain amount of time. And that's going to be that equation.
Right.
Okay?
Okay, well, thank you so
All right,
much.
Taryn, I'll talk to you next Monday.
All right, sounds good.
Bye.
Bye.